Yeah, so we are ready to start the holography session 2. So the first talk will be by Professor Inbarasan Muniraj. Will present about the role of deep learning in optical imaging. Let's hear about Professor Muniraj from Android.
Okay, so I would like to introduce Dr. Inbarasan Muniraj. He holds a PhD degree from University College Dublin. He also holds a Master of Engineering degree in Optical Engineering from Chosun University, South Korea. And he also holds a Bachelor's Engineering degree in Electronics and Communication Engineering from Anna University, Chennai. He worked as research scientist in Gwangju Institute of Science and Technology, South Korea. His PhD was sponsored by the prestigious Government of Ireland under Postgraduate Scholarship Program for the year 2014-2017. After a year-long postdoctoral research experience from UCD, he worked for Intel Corporation in Ireland on a few different roles for 2.4 years. He is currently implementing 2 Government of India's Department of Science and Technology sponsored projects, one with Science and Engineering Research Board and one with International Cooperation Division. His primary research interests are developing a non-invasive imaging system for low-cost biomedical applications. In addition to this, Dr. Muniraj is also interested in instrumenting low light level photon counting imaging systems for various imaging modalities, such as 4D light field imaging and holographic microscopy. He has authored over 40 publications in peer-reviewed, reputed journals and delivered talks at various prestigious international conferences. He also authored a book in Spotlight series, and he is an inventor of 2 Indian and 1 United States patents.
Thank you, Andrew, for the introduction. Let's welcome the speaker, Dr. Inbarasan Muniraj.
Thank you, Dr. Balasubramanian and Android. Thanks for the long and nice introduction. So let me share the screen and please let me know if it is visible. I hope it is. Is my screen visible? Can you see
yeah,
my
screen? It's visible.
Perfect, thank you. Yeah, so for today's talk, I wanted to talk a little bit about the deep learning. Part of the reason being, as I was introduced myself, I have my engineering undergrad from engineering discipline, and for my postgraduate, for my master's, I had my master's from computer engineering. And for my PhD, I worked on optical imaging systems. Therefore, I wanted to combine these 2 interdisciplinary things into kind of merging them to see which benefits which. So the intention of this talk is to show you a little bit about the deep learning, which is most of us probably started off investigating in. Right, so I wanted to talk a little bit about some of the basics of deep learning and some of our recent research results which have obtained from this applying deep learning techniques on some of the conventional imaging systems. And again, myself, Dr. Inbarasan, I'm an assistant professor here in Alliance University, Bangalore, which is in India. So before I go and talk about some of the imaging systems as well as the techniques that we have used through the deep learning, I wanted to briefly introduce what is a deep learning technique and how do we implement this deep learning technique as in the context of optical imaging. And then I'll show you some of the techniques that I have used, to get some of the results, namely image denoising, which is one of the primary, research interest among optical scientists. And the second topic that I would like to talk a little bit about on is off-focus removal, which is specifically for this 3D integral imaging, which is one of the techniques, but still, you can relate this applications of this off-focus removal in almost all the optical systems. When we talk about this deep learning is nothing but a subset of machine learning, and it's kind of a network which has 3 or multiple connected layers. Essentially with 3 or multiple connected layers. What this network does is that we just try to mimic the human brain, where we have multiple neurons which is connected in layers. As in, every neuron transmit one information from one place to another place. Similar to that, we wanted to mimic a system in computers. Therefore, we call this system as a kind of a a network which mimics the human brain, and therefore it tries to attempt learn first of all, just like human learn from seeing several things and learning several things. Now it first learns things and then try to take a prediction or try to give us kind of an output based on its learning. Because of this, because of the versatility of this particular deep learning algorithm and the availability of this parallel computing such as GPUs these days, the applications of deep learning or the deployment of deep learning become ubiquitous. As in, you could name any scientific research field where you can see the applications of deep learning have been started investigated, or at least they might have published several research articles on top of whatever they have been currently doing. Due to that, optical scientific community has also have started investigating some of these deep learning networks for several applications. As I wanted to highlight some of the portions which Professor Anand have introduced in the introduction section in the morning, where he has talked a little bit about some of Professor Oskan's work. Similar to that, there are several works which have been published based on this deep learning, such as super resolution microscopy, lensless phase retrieval imaging scattering media, computational ghost imaging. There are several techniques people have started investigating the applications of deep learning using these conventional operating systems. In general, or in principle, if you wanted to talk about a deep learning algorithm or the implementation of deep learning algorithm, it follows in two ways, or this can be implemented in two ways. One is a supervised learning. The second one is unsupervised learning. Whenever we say supervised learning, as the name suggests, we are going to supervise the learning as well as we are going to kind of train the system using what we call as a labeled data. That means we give a network with a labeled data. Suppose if we wanted to label or classify a cat out of multiple animals, we feed the network with the multiple cat images with multiple different perspectives. Therefore, we call this as a labeled data. So you label the animal saying that this is the cat, and whenever you see a similar animal in this group, you find out as a cat, right? So that's what we call as a supervised learning. In contrast, a supervised learning, where we say that we don't use any sort of a labeled data, so we don't give any sort of label, but we let the algorithm or we let the network to take its own decision by looking at some of the patterns that that can find it from an image itself. Let's say if I give a bucket of ball with multiple different colors of ball inside a bucket, and I ask the network to train it on its own, and then wanted to take some sort of a prediction, what it does is that it looks for some sort of a feature or usual features. Let's say it looks for a color. Let's say if I have 10 balls in red color, 10 balls in green color, it looks at the colors of this object, and then it takes a decision automatically. When the new ball comes in based on a color or any other feature that you might have trained itself, it could take a decision. That's what we call as unsupervised learning. So main difference between the supervised and the unsupervised is that we don't have enough labeled data set for unsupervised learning, whereas in the supervised learning we feed the network with thousands and millions of labeled data to make it more accurate. To brief introduction about the technique, the optical imaging system that I wanted to talk about is integral imaging. Integral imaging is kind of an optoelectronic device, optoelectronic system, which is kind of an alternate to the digital holography. Right. So what we do here is that we take a multiple two-dimensional images of a same 3D scene, and then we try to combine them in a perspective. Therefore, we can produce a 3D images better. There are two ways of employing this 3D integral imaging system. One is to use this lenslet array or a lens array with which is packed of micro lenses in an array format. Or you can move the camera. I'll show you one of the setups in the upcoming slide. But there are two ways, as I mentioned. One is the lenslet array, which is of the single shot, or by moving the camera, you can take a multiple images, and then once you have the multiple images, you can easily combine using some sort of a computational algorithm. Therefore, this integral imaging can be classified as a computational imaging system as well. If I wanted to differentiate this single shot and the multiple shot images, as we can expect that single shot is quite, because we just have to take one image and then process it later on, whereas in the multiple or moving camera shot, we have to take multiple images by moving the camera physically or mechanically. Therefore, you take multiple images and then you capture multiple images and then you reconstruct it using those images. But the former approach with the single shot would provide faster, but which often suffer from a poor resolution, whereas the latter approach, which is the multiple camera shot of the moving camera shots, which provides the which provides the satisfactory resolution with the higher computational complexity. This system was proposed back in 1908 by Professor Gabriel Lippmann, in one of his paper, La Photography Integral. You can see it in the reference one. It's been there since 1908, but it got kind of picked up after early 2000s, right? After 10 years of research on this integral imaging, people have started investigating of this integral imaging for various applications such as object detection, automatic object detection, underwater imaging, whatnot. There are multiple imaging systems have been proposed using integral imaging. What is most interesting, or what is more relevant to this particular talk, is that this particular paper, which I have referred as the second row, right on the subnote. Right, what we call as photon counting imaging. So back in 2008, Professor Ben Taukoli as well as Professor Javedi from University of Connecticut have introduced or demonstrated a technique called the photon counted integral imaging. What they have done is that they followed this photon counting principle, which we all know from the basics physics. They have followed this principle to capture this limited number of photons in a scene and then try to integrate with the conventional integral imaging system. And we call the system as 3D integral photon counting integral imaging. So as we know that photons, whenever we wanted to capture an image in an imaging sensor during particular time, the photons travel in a random way. It doesn't travel in one go; it travels in multiple random ways. Because of this spatial and temporal randomization, because we take it in both the spatial and temporal data set. Because of this randomization, the photon counted images that we capture, usually represents a binary image, as in you either see the scene or you don't see the scene. Just like it can kind of a binary, either it's in a pixel or not a pixel, zeros or ones. But this 3D, although this is, this looks kind of a binary, this 3D imaging system is, widely used for several applications where, one of the main applications is biomedical imaging, where we don't have too much of light coming out from the, human body. Therefore, with the limited number of photons, we'll be able to capture, better images. One of the main limitations of this photon counting systems is that the images that are produced by this PCIA, which is photon counted imaging systems, looks more into the kind of a degraded into degraded very much because of the noise that prevalent in the scene. I'll show you some of the images in the in the upcoming slides, but one of the main limitations of this PCIA is that too much of impulse noises. The other limitations of, not the limitation, but other, shutback of this particular technique is that this technique reconstructs images which contains both the focused and off-focused voxels. As you can see, in any reconstruction technique of holography, you would be able to see a particular portion as a clearly focused, rest of the focus, which are not in the field of view, would be off-focus. So the same applicable here as well. We have both the focused and off-focused voxels. These techniques can be easily, eliminated using some of the conventional techniques. But in our research, we have shown, I have already proposed some of the techniques to, remove the, photon counted noises as well as the removal of off-focused vocals. But in this work, I wanted to show you, how do we use this deep learning technique to remove these artifacts. And as I mentioned before, this is a 3D imaging system, which you can see it on the left, where you have a 3D object and you have multiple camera array. As I mentioned, you can either take a multiple camera array or just a single camera and move the camera both X and Y, and take multiple images and use the photon counting simulations. Then you can get the 3D photon counted images. One of the main limitations of any optical imaging systems is that we don't have multiple images, as a large data set is not available. In producing synthetically multiple images or large data set is a time-consuming task. For that particular reason, I wanted to use some sort of an unsupervised network which doesn't take a larger data set, but will be able to produce a better results with the limited number of data sets. And this particular network is known as an UNet, which is one of the deep learning networks, and which is end-to-end unsupervised network. As in, just take a single image. As you can see here, only one 3D nice image will be inputted to the network, and after the several step process, it will be able to get back our deniced images. Since we don't have multiple images, what we do is that we do what's a patching. We take a small amount of an image. Let's say you have an image of 1000 by 1000, and then you take a small patch, probably size of 3 by 3 or 4 by 4, depends on your application. For our case, we have taken 8 by 8. As long as you have this multiple patches in 1000 by 1000 images, you would probably have multiple data sets. So every single patch would resemble a single image. Therefore, from that particular single patches, we'll be able to learn better, and then we can take a decision better. And that is our network. And I wanted to show you some of the results of that particular one. So this is what we call as a reconstructed image on your left, which is A. We have used two objects, object 1 and object 2, which kept at two different depth locations. And when I wanted to reconstruct the image using the conventional integral imaging reconstruction algorithms, I get the B and C. The B, as long as you enter the depth location that you wanted to see clearly, that particular depth location object will be clearly focused. The other object is not focused. As in the image B, the first object was focused, the second object was off focused, because they both kept at two different locations. Likewise, in C, the first object seems to be off focused, the second object seems to be focused. As you can see from both B and C, either one of the objects will be clearly visible, because every time we reconstruct, we tell the depth location. But whenever the same imaging system has been implemented with the photon counting system, this is what you get to see. So A1 and A2 represents the same images with the photon counted systems. Whereas you can see the PSNR values are very low, which is 6.62, which is it's not acceptable. And the middle B1 and B2 shows the conventional technique, which is TV denazing, which people have used previously to denazing the system. And the extreme right C1 and C2 shows our own network results, where we have outperformed conventional systems, and we are able to get better denazing results. Before I move to the next topic, which is from this slide, it should be clear that, as I mentioned, the reconstructed scenes would have both the focused and non-focused work cells. I wanted to remove them for the better scene representation. So what I do is that, this can be implemented through, some manual algorithms, but I wanted to do that since I have already done that with some sort of manual calculation. I wanted to do that with, with the help of deep learning. So this is the proposed deep learning architecture, which is one of the simplest architecture that we can ever use, which we call as a DNN, Deep Neural Network, which is one of the earliest deep learning network, right? Which is connected with multiple layers. As I mentioned before, it resembles the human brain. As you can see, every single neuron is connected to each other. Therefore, it mimics the human brain. With the help of this particular network, we were able to remove the off-focus vocals. On this data set, as you can see, every depth location, for instance, A, at 280 millimeter and B 298 millimeter. So as you can see, every depth location, only one portion is clearly visible. Rest of them is blurred or off focus. So what I do is that take this whole image and feed into the network. Since we have trained the network enough to remove the off focus points, what we get is that we get this particular scene. So when you try to combine all these images, you would be able to see a complete reconstruction of focused points, whereas the rest of them will be kind of a blurred or blacked out. Therefore, you get to see the clear object, which is only focused, right? This is predominantly useful in biomedical classes, in case if you wanted to track some sort of a molecule or some sort of cell that is traveling from one place to another place, which in other sense you won't be interested. Therefore, if you would be able to use this kind of a technique, you'll be able to clearly track that particular cell or whatever microparticle in a given scene. So that was the second set of results I wanted to present today. Right. With that, I wanted to conclude the talk. I hope I have taken enough time. So DL has led, as we all know, that DL has led to a paradigm shift from a physics-based modeling to a knowledge-based modeling to solve several problems in optical metrology talks. In particular, DL is suitable for other problems where we don't have too much of data because of the physical complications that we have for this optical imaging system or any metrological system. And some people think that some sort of this artificial intelligence algorithm might replace the conventional technologies, but I don't think that would happen, because DL is there to kind of assist us in boosting the performance of whatever we already have, rather than just replacing that. It is therefore expected to extend such investigations on different type of imaging modalities, such as holography, microscopy. We have started investigating something on holography now, but it is widely used for holography and microscopy as well. I wanted to thank the financial support from the Science and Engineering Research Board, which is supported by Department of Science and Technology, Government of India. And then some of this work were carried out when I was with SRM University AP. Therefore, I wanted to thank them for administrative support and the scholars who worked on this particular research, Ms. Vinila and Mr. Sujit. And that's it from my side. I hope I didn't take too much of time.